Hi, my name is Neha, and this is our 469 project. So we observed the bandpass filter response and calculated the resonance frequency and found that the output voltage at the resonance frequency is equal to that of the input voltage. And then we simulated this circuit to see the response over the frequency range from 1 Hz to 100 megahertz. And then we redid the simulation, doing a parametric sweep and changing the capacitor value. We noticed that an increase in capacitance results in a decrease in the resonance frequency. This is a result of the capacitance being inversely related to that of the frequency as represented in this equation right here. Then we simulated the circuit again with a parallel resistor to the LC and saw that the impedance drops when it is placed in parallel and that it no longer functions as an open circuit. And if we move the resistor to be in series with the inductor, we would see that the current passing through the inductor would be decreased due to a higher impedance and that it would behave as a low pass filter.
Hello, my name is Nabiha, and I'll be explaining part A of question 2. So we ran the simulation and we got these values. You could see they're very similar to the hand calculation. The only big difference you can see here is probably the small signal gain, and that is because of rounding errors during the hand calculations. This is the figure that we have simulated. Again, just to put the values in here. And as I explained above, there's changes a little bit here and there, especially for the small signal gain because of rounding errors in the hand calculation. And these are the graphs that we get when we apply the AC signals for the AC sweep. And there is a glitch because the impedance is at its maximum and it's not really being filtered. When we apply the amplitude modulation signal to the input, we get this graph right here, and we can see that it's at a higher scale, so it appears a little bit smaller. The gain of the circuit is this. We just did B out divided by B in, and this is a detection circuit that we simulated, and as a result, we get this simulation as a result.
Hello, my name is Ali. For part B, question 1A, we find the values by hand calculation by doing DC analysis. On the baseband amplifier, we're given the Q point and we assume beta to be 160. We do the Thevenin equivalent and find RE to be around 2.5 kilo ohms. We find RC to be around 530 ohms and RE2 to be 16.56 ohms. In part B, we simulate these values. However, we change RC so we can get a voltage gain of 20. We keep all the other values the same, but this change was necessary to fit the design requirements because it called for a voltage gain of 20. In part D, we can see the output waveform and the input waveform, and we can see the amplifiers working because the output waveform has a much greater amplitude than the input waveform. In part E, we perform an AC sweep, and in question 2, for the output buffer, we assume R15 to be 40 kilo ohms. We're given the Q points for both transistors, so we find the collector base and emitter currents for both of these transistors, and we're able to find R17, R15, which was already assumed to be 40 kilo ohms, and R16 we find out to be around 9,000 ohms, exactly 9,328. And we set our capacitance as 1 millifarad.
Hi, my name is Wajahat. Today I'm going to be talking about part B, question 2B, till part C. So as you can see here, we have a buffer. So when we're simulating the buffer right here, we found VCE for the first transistor and VCE for the second transistor and IC for each transistor as well. We also found the voltage at this point, so VB, and this output voltage as well after the capacitor. The differences between the calculator and simulator were because of rounding and our beta values as well. So when we inputted a AC signal, we got this small signal right here, which is an input signal, and this larger signal shows the gain of the output signal. And then when we did an AC analysis, we got a linear sweep. When we did a log scaled analysis. So when we connected the baseband amplifier, with the buffer, we got this signal. This smaller signal right here is the input signal, and this bigger signal is the output signal. You can see there's some clipping over here. In the end, when we connected the whole circuit together, and we inputted a modulated input signal, we got this blue line, which is our output signal.